Okay, let's get started. So, before we dive into today's content, we will talk about what we have learned so far. We have learned all kinds of software vulnerabilities so far in this class, starting from buffer overflow, which also include other types of buffer overwrites or alpha-bound overwrite or overread. We're talking about format string vulnerability, which you can write to arbitrary memory or even read from arbitrary memory. Heap vulnerabilities, which is very complicated because heap itself. Thousands or even more lines of implementation. There could be a lot of bugs there and grease conditions sometimes also come with problem. Then we'll also learn several different kinds of exploitation techniques, starting from return to a function in the address space, return to a C library function, then we develop our own shared code. Then we learn how to do return-oriented programming, which you do not need to return to a full function, but just return to some code sequences, some gadgets in memory, and those gadgets are not even necessarily emitted by the compiler. They could be some random bytes, data bytes in the memory, and the CPU can interpret them as valid instructions, right? You also learned how to mitigate those kind of attacks at hardware, OS level, and also compiler levels, from non-executable stack to control flow integrity to address space layout randomization. So when we look back, we think about the workflow of exploitation. Then we think about, we first try to discover and also understand the vulnerability. And you have been doing so by reading the source code or reading the binary code. Reading source code, I've been doing that 9x9 source code. Binary code is OBJ down, binary ninja, DBB, to try to understand instruction by instruction, right? I've been doing that. I've been doing a lot of calculation to say whether one instruction will influence a big memory regions and whether that will lead to some kind of vulnerabilities, override a local variable, override the return address, or other function pointers. So we have been doing that manually, okay? We also have been assess if this is exploitable, what kind of mitigation are there? Even if there is a buffer overflow, but if there is non-executable stack, which means you cannot inject a shellcode there, you need to look for other approaches like return-oriented programming, right? So after that, you will write your own exploit payload and try to bypass existing protections and eventually capture the flag. We even learned many different ways to capture a flag. You can get a shell, which you get full control of the computer as a share of root. You also can make some other system calls like change mod, which assume the permission of a file, the flag file, right? When you look at this, I guess you have a feeling that the first step, the discovery and understanding the vulnerability part, seems easier than the other part so far, right? And you have that feeling that's because so far the vulnerabilities we are looking at, they are very obvious. The example code I'm giving you, I wrote every one of them to show you the vulnerability. So that's why the vulnerability is very obvious. The code is short and simple. It doesn't have other functionalities, but just to show you the vulnerability. For example, this is the vulnerability we looked at the first half of the class. Now you look at this, you will say, you know many different ways to exploit this. And the vulnerability is so obvious. There's the main function calls valfoo, then calls printf. And the valfoo has a local variable buff. The compiler, the state source code level asks for 40 bytes. Compiler may give it a bit more. Then you see the dangerous gets function that will take input from the standard input. and the get doesn't stop unless the user press enter new line or end of file, right? So then you know that we can overflow the buffer, and if we can overflow the buffer, we may overflow many different things, including the return address, and even addresses much higher than, right? So the vulnerability here is very obvious. However, in real world, identify real world bugs is not necessarily that easy. Right? After you discover a bug, we try to think how you exploit it. But discovery, understanding the bug itself may not be easy. So here I give you another example. So this is a real world bug. There is a CVE assigned to that. CVE is, you can consider that as a database of real world bugs. So there is a year assigned to that and a bug ID for that. So this bug was going to widely use the C library for passing XML. And this is used by many Linux applications, browsers. And there is a function for the XML printf element content. And this is the code. It's almost everything of the code. And let's say if we can find the bug compared to what we saw before, it's not that obvious, right? So the function itself takes, let's say, 1, 2, 3, 4 parameters. The first one is a pointer, the buffer address, then the size of the buffer, then another content, and that is another built-in, say, structure. It's a complicated structure, then there's another integer passed in here. So the first thing this function does is to compute the length of the buffer right now. So how many data, how many bytes have already been written to the buffer. So that's the length. Then if the length is bigger than size minus 10, then we're going to return. The size here, obviously, it's the size of the buffer. If we have already used more than if there are fewer than 10 bytes still available, then we're going to stop writing to the buffer. Right? So this security check here looks very generous. It's much more conservative than all the security checks we are thinking about. Right? We have always to check the size of the buffer and what we're directed. So here, very conservative. If you have just a fewer than 10 bytes, the code is not going to write here. So it looks like very safe. But there is actually a bug there. So then after that, we were based on the content of the message, we're going to do several different things. We're going to add some strings to the buffer. So here we're adding 7 bytes, a hard-coded string. Here we are adding the name. Okay, so the name of them, we don't really know how long this is. So potentially this is a problem. Then other cases, we're going to add the left parenthesis there. And the most importantly, there is a recursive function call. In that case of XML element content all, there is a recursive call of this function again. And after that recursive call returns, we're going to append another 3 bytes here. Anyone say some vulnerability here? Not that obvious, right? Okay, so the problem here is the recursive call is using the same size. So box size, that size is not reduced, but you may have already did something else to reduce the size. And the check of that size is only at the very beginning of the function. And when that recursive call returns, the size of the buffer is already reduced and eventually will not overfill. Right? So there is a concrete way to trigger this bug. Let's say when we first enter this function, the length is size minus 11. So the length is greater than size minus 10 in this case, right? So we're not going to return. We pass the security check. We keep going. Then we go to the OR case. Then we are going to the recursive function where we are going to fill the buffer. When we fill maybe 4 bytes there. Then after that, we return, we fill another 3 bytes. Then in total, buffer is already at size minus 1. It's different from what we first checked. So this is also related to the time to check, time to use vulnerability we talked about last week. So then, if there's another message coming in to use another byte, then we're going to override the buffer. So even if that piece of code, the statement looks like we are going to do some very conservative security check, the buffer overflow can still happen. And just about reading the code, we do not necessarily have realized that. So there are many other reasons why manually discovering bugs like this is not feasible. First of all, they are not that obvious like that one. Even if it's in front of you, you do not realize there is a bug. Second, the sheer volume of source code we're talking about is just infeasible for everyone or group of people or just everyone together to find all vulnerabilities, find all bugs. The Linux kernel already has 40 million lines of code, and every release cycle it grows like 70K. Windows 10 have more than 15 million lines of code. Mac OS even bigger, 18 million lines of code. Right. So most of those code are C code, Object-C code, C++ code. Difficult to understand in the first place, let alone identify bugs with your bare eyes. So that's why we need some automated approach to discover those bugs in a very fast way and a very scalable way. So GitHub has been scanning all the open source projects in the posting to find bugs, and it reports to users. We may have a bug here in the project, maybe using vulnerable libraries here, right? So there are many different approaches. There are static approaches. There are also dynamic approaches. So today we were mainly talking about the first step, how to automatically discover these bugs and scale using a dynamic analysis approach. And the approach we will talk about today is called fuzzing or fuzz testing. So this is by far the most scalable, fast approach to find the vulnerability. There are many other approaches. Some of them are very slow. So the students who took computer system class listening last semester, 3650, you use the Week in your second project. Week can also discover many bugs. However, Week is very slow. When you run a program under Week, we're talking about 30 times or 50 times slower than the original program. But fuzzing, we can do it. Fuzzing technically, you can just run the program without changing it, using the same speed. But the fuzzing we talk about today, we were changing the program, so we were just 2 times or 3 times slower. So still 20 times faster than towards that volume. So the idea of fuzzing is actually very simple. We just want to design some approach to generate random, unexpected, or mutated input to a program or just to some functions. And those inputs will trigger the program or just the functions to malfunction to crash. So it will manifest as a bug. Then we just go there to analyze what is the root cause of the bug. We know that we do. We just analyze what the root cause of the bug caused the program to crash. The bug caused the program to just enter an infinity loop or come there, or there are specific memory errors we're looking for, or just some undefined behaviors. So that's a basic idea, very simple. Random data feed into program, right? Of course, random is a big word, you all learn probability, right? So if we wrote random data, it doesn't mean it's uniform made, it's simply random data. We want to find a random data in some special regions in the infinite space, which are more likely to stabilize, right? So this technique has been applied to all kinds of software, from web software, network protocols, binary software, we're looking at. Obviously, in this class, we focus on binary software. And there are many different funding approaches. The basic idea is that some kind of random data feed into the program to make the program manifest a bug, malfunction, right? So in its very simple or simplest form, I call this a naive fuzzing approach. We want to fuzz some binary programs. Let's say we just want to fuzz Linux or Unix utility command line tools, ls, cat, strings, obj dump, the tools you have been using in this class. How do we find bugs of that? We just generate some random data. The kernel has the device random or device U random, several devices to keep generating random data. We just apply those random data to those programs. So most of those programs takes input from S to the E. Some of them also take input from argument, so we can also take them into argument. Then we just say if they crash, or they enter an infinite loop, just 100, right? Or they may just exit and the return value is 0, means that it's no bug. Right? So that is a very simple, naive way to fuzz this program. And it's very simple to implement that idea. So this simple script here, 6, 7 lines, we're just to do that job. We first define a target. What is our program? ls, sort, string called string, right? Then we just enter a while forever, and this loop will get some random data from device URAM or device RAM. Those are two random devices on Linux. One of them is much faster than the other one. However, the slower one has better quality in terms of randomness. Then we just get the first 500 bytes of the data, and we just feed it into the target, right? So we do not really care about the output of the program. So that's why we redirect the output just to device now there. We don't care. We also do not care the STD error messages. So we redirect that into what? That's this time. So what we care about is how this program returns. So when you write a C program, everything goes with the plan. You just return 0 and so if something goes wrong, we usually return 1, return a positive value. So some of them probably return a negative value, return -1. Typically in Unix, we're not supposed to return minus number, it should return a positive number. But the C programming language doesn't allow you to do that because the prototype of the main function, the prototype of the return value is C, right? The return type is C, it's not unsigned C. Now, Linux will treat that as unsigned integer. But when we try to get what was the return value, so in shell programming, the $sign question mark gives you the previous command or program return value. So when we get that of the status, then we just check what is the value of that status. If that is a segmentation fault, which we are familiar with, then the return value is supposed to be 139. That's because in Linux, when your program returns, you're supposed to return 0, 1, those small positive numbers, if the program return or exit normally. However, if that program was killed by a signal, let's say there is a memory function, there is a segmentation fault, then the kernel will kill that program, and that program will have a different return value. In this case, if it's say segment, it will have the signal number, which is 11 plus 128. That's why you get a return value of 131. So there are many other signals we can kill a program, not only segmentation fault, it could be signal board as well. We also talk about that before. So by doing this, you can find what kind of input can trigger vulnerability, can at least crash the program, right? So this is actual approach proposed back in the 80s. And there was a paper published just using the approach to test the reliability of NEU's utilities. So the paper didn't really own the term Fuzzing, but this is the first time Fuzzing was really used in real world utility those tools. So the paper was published in 1990, and we started working on this late 80s. So, however, this approach is naive. Okay? It doesn't work very well. So there are several reasons that are not working very well, and modern Fuzzing approaches will address those issues. The first one is there is no coverage implemented. So in the previous approach, you treat the target program of a black box. Yeah, that's a feeding into the program and to say if it crashes, right? In that approach, we didn't look at the program itself. We didn't keep it on board. We didn't try to understand what the program is doing. We just feed random data. So we do not really know whether an input reach some interesting part of the program. The program may have thousand lines of code. Your input may only reach at the very beginning and quickly make the program to exit. It didn't really touch deeper states, deeper code in the program, right? So, and there is no way in the previous approach for us to guide the input to reach the deeper state. And most of the input, like I said, they were just reach a very shallow state, and they were being rejected by the program anyway. Then we are wasting a lot of time and efforts by generating those meaningless input, right? Then if we find a good input, so a good input here means an input that reach a deep state and find a bug, then we do not have a way to build more input on top of this one, right? So this input can trigger this bug for some reason. So we should utilize some kind of characteristics of this input, build on top of this, change it somehow, so we can trigger more bugs, right? If this input can reach a deep state, by changing it a little bit, we can still reach a deep state, but maybe different branch. So those are the problems of the simple approach I just talked about. So think about this. No matter if LS is object design or any other tools, or just even a function we talk about there, the input space is almost infinite. Most of the function we talk about, the input space is almost infinite, right? Especially if there is a pointer or whatever, if there is a buffer, infinite. And if you want to find a bug, your input should trigger some specific portion of that function. If you do not even execute that portion function, you cannot find a bug there. After you reach there, then only particular input can trigger a particular bug. So the input you are looking for, which can trigger the bug, is a very, very small portion of the infinite into the space. And we want to find that. If you just randomly guessing input, generating input, and the infinite space, you will be wasting a lot of time. So the science here is how to get it there fast and quick. So that's why in this class, we learn a modern coverage-based fuzzing approach. And we will look at a very particular tool called AFL, American Fuzzy Loop. And a little bit of history of this. So the tool was first developed and released in 2013 by Mika from Google. And it introduced the concept of a coverage guided approach. And this is the foundation of modern fuzzer. And we have been using this. There have been several fuzzers developed based on similar idea. And even in our lab, we are developing all kinds of fuzzers based on this. So the original author of this stopped maintaining this project. And so right now, this is a community effort to keep developing this. And the community fork of this project is called AFL++. It's called AFL++. However, the tool, if you run the tool, it still shows AFL, American Fuzzy Loop. That's it. Okay. So when you run this is the interface. We will talk about the details later when we look at several concrete examples. So this is the architecture of this. We're not going to talk about every bit of this, but just several very important modules of that. The very first module we want to look at is the instrumentation part, and also the coverage bitmap. And the goal for those two parts is to get coverage information, which is the very first fallback we talked about with the naive approach. So what do we mean by that? Okay. We use this simple example to showcase how AFL works. And this is changed from our overflow local 4 challenge, very similar to that. So you already know how to identify the bucket here, and you already know how to find the hashing flag for this one. But now we are trying to use an automated approach to discover the same bug and try to understand how this automated approach works. We have the main function. The main function calls walkthrough. Walkthrough, the first one has a local variable, is admin. It's an integer, so 4 bytes. Even for the voting machine, usually it's 4 bytes. Then there's the buffer, 16 bytes. After that, we have F read, reading from std. The F read here is carefully designed. So the F read here will not overwrite the saved RDP or return address. It will only overwrite the is admin local variable. So the reason we have 32 bytes there is because the box here has some alignment. The compiler will give the more bytes. So then the program just compare what the user input to the buffer, whether the input start with admin, those 5 characters, doesn't have to be just those characters that start with, because we're only comparing the very first 5 characters with string uncompared. If the input has admin, then we're going to set the local variable is admin. Then there is another check. We check if admin is not 0. If yes, we just print flag. Okay. So print flag is the function we have been using many times in this semester. You probably didn't say the source code before. Yeah, but we have been using this function a lot. Right? The source code is very simple. There is a pointer, a file. There is a local buffer, which is kind of big, 256 bytes. Then it tries to open the flag file in the root directory. Then it try to check if the open was successful. If it's not successful, it says cannot open the flag file. This is not successful. Maybe you don't have permission to do so. Right? If you are not running this as a root, you don't have a permission to open that. You also can get this message if the file doesn't exist. Otherwise, it will just read the flag, then print it out for you, then close the file. That's it. Yeah. So this is the one we are familiar with. So let's say how we can find the bug here. So first of all, what kind of bug is bigger? But we cannot overflow the return address, like we said. Or we can overflow the admin local address. There is a bucket overflow, but when you overflow the admin, each admin local address, we will get a segmentation. Right? Even if the flow is successful, we're not going to get a segmentation point. When we overflow the return address, eventually we may get a segmentation point is because the return address is basically a token. The CPU will start executing from where the return address is. So we will return reference back. And if the place where the referencing is not real, then we get a segmentation point. Right? So here, the is admin is a local variable. It is writable. So by overriding that, we will never get a segmentation point. Right? So this is a make file I used for this project. We have been using GCC for the most part. So today we're going to use LLVM, which AFL has been using LLVM. Also developing LLVM compiler concepts is much easier than developing GCC compiler concepts. So for all our research projects, we use LLVM. So the C language compiler part of LLVM, the tool is called CLAM. Okay, so the command is CLAM, but it's actually the LLVM. Then we have two more commands here to compile two different versions of instrumented program, so AFL can find it. So this one is a different command. It's called AFL -plan -file. So this is the AFL compiler. First of all, it is a compiler. You can see the options we're giving here is the same as the options we're giving to GCC at the time. Okay, so this is a compiler. But this compiler will generate the program that can use AFL to file. We'll talk about this one later. So this tool, first of all, it is a LLVM based compiler. Basically, they developed some LLVM process there, and those process were instrument code for the target program. So the idea of instrumentation here is just to adding or changing instructions program. We talked about this before when we talked about shadow stack, when we talked about control flow integrity, right? So those are also implemented as compiler process. So the software developers do not really change their source code. Your source code goes through the compiler with those particular compiler process. Then the machine code generated will be automatically protected, right? So software developer doesn't need to do anything special. Here, the same thing. So the goal of this compiler is to instrument many different things. But the most important one is it tries to track which branch edges are covered and executed by each input. Okay. And branch here is defined as a point of the program. Okay. We're talking about machine code here. A point of program where the control flow can go to more than one places, depending on the condition. Right. So what kind of, think about the x86 instruction. Then what kind of instructions were introduced branches? We go. If statement, but that's SQL, right? Machine code. No. No. Compare is actually before that. Jump is close, but technically we're talking about a conditional jump. If it's an unconditional jump, the target is only one. You do not have more than one target, correct? But if you have a conditional jump like J and E, jump not equal, then technically you have two branches. What others? More than one target. Control flow instruction, more than one target. How about call? Do we have more than one target? Not necessarily, right? So the call, the target could be hard coded. But we're talking about indirect calls, indirect jumps, where the target is a register, right? So in that case, the register value is only determined at runtime when you are about to execute that instruction. So by doing static analysis, you may have multiple targets, right? So those can be considered as branches. Then we use a shared memory. So shared memory here means the shared memory between the program under Fuzzing and the father itself. They use a data structure called feedback to record what kind of edges are taken. The edge here is basically from one basic block to a different basic block. And each basic block ends with the branch instruction to just block it off. So when the father finds that this input discover new edges, it means this input is interesting. The input is reaching to a new state or deeper state of the program that other input hasn't been able to do so, right? Then you are saying this input is interesting. I will keep mutate this input based on this. And the command to do that is this way. Okay. So this is a compiler. The compiler program, then you get a compiler. So this is same as what GCC or LLVM command. So when we use this tool, AFL fast to compile this program, okay? This is the output we get here. So your output instrumented 6 locations. Right. Only 6 locations. So now let's take a look why it instrumented 6 locations and where 6 locations. Go back to the source code again. Now, I marked several locations here. I marked 8 locations here. Let's go through each of them to say if you think we should instrument it. Okay, so we are going to instrument the ratchet. Okay, ratchet means it has multiple targets. So let's say if we want to instrument it. The first one is a function call. So the first two, they are not necessarily in statement. The first one is active statement, there will be assignment. Then the function called F3. Should we instrument the F3 function call at a binary level, or is regular instruction level? It's just a call. Then what is the target of the call? Is it hard coded? Or right? Most likely it's hard coded, right? So the destination is there's only one destination, right? So this is technically not a branch, right? The call to F3 is not a branch, so we don't really need to instrument there. Right? The concept of branch here is slightly different from the branch where the branch concept we have been using in the first concept class. So previously we were saying call, jump, they are also branches, but here branch means only more than one time. How about the if statement there? We are going to compare our buffer with a hard-coded string, the if statement. If we take this branch, we are going to go here, right? If we don't take this, we go here. So how many targets are there? There are two targets, which means we need to somehow instrument here. Okay, we actually were instrument both targets. We were instrument here and here. So after that, we have another predicate. We check if the enemy is 0. So because it's comparison, there are two branches again. One goes here, one goes here. So here should be instrumented, here also should be instrumented. Then we have the print flag function. Print flag function also have F open. Only has one target. We don't really instrument that. Then there is a if statement. That's why we need to instrument here and also here. Okay. So those are the places we AFL needs to instrument. Then let's take a look at how AFL actually instrument that. So I already compiled the code. Then we just use binary ninja to do this. Look at this. Because the instrumentation is very complicated, that's why we're not using OBJ today. We just use binary ninja to look at the pseudo C code, which will be easier to understand. So the version you are looking at here is not compiled from GCC or LLVM. So it's not the production version of the program. It's compiled using the AFL's compiler. So I call it overflow local 7 AFL. Okay. So you'll still have the start function. Start function eventually calls the main function, right? So from main function, there are function call to vol foo. Okay. So and this is what the vol foo looks like. Compared to the uninstrumented one, this is much more complicated. So let's take a look at this. First of all, you notice there are some local variables for the starting with AFL. So those are obviously instrumented by AFL. Another very interesting thing you notice here is, do you see a function called to reflect? Look for that. Okay, you move it. Let's just look at here, this one. This is vol foo. This is not print flag, right? In print flag, we will try to open the file. If we cannot open the file, we will print out error cannot open the file. Right? Well, this is vol foo. Why we are seeing that string get printed here? Print flag itself is not a branch, it's a function, right? Okay. So imagine the previous code we compiled directly from GCC. Vol foo should have a call to print flag, right? It should not have this particular statement just to print out, because this print out, the print hooks should be part of the print flag, should not be vol foo, right? Right. So the reason the compiler is doing this is actually not because of AFL. The compiler may make those kind of choices time to time. So what happens here is the compiler decided to use that print flag function of an inline function here, which means it will directly expand the print flag function inside the vol foo function. Okay. So vol foo doesn't make a function call to print flag. Instead, the call to print flag will just have the content of the print flag function. Okay. So this is obviously the case that we cannot open the file, right? Then there are other cases. Let's say this one. This one is the open the file successfully and print it out. Okay. Then we should have the cases to compare whether it is atomy. So this is actually to compare if it is atomy. So if you think about this, we can simplify this program as several basic blocks. The main function only for molecule, the molecule returns. There is no branches in the main function. Molecule will call F3. After F3, we will compare the buffer. After compare the buffer, you will compare whether the F open is successful, right? So the basic block looks like this. There are several basic blocks. First is after F3, after we compare, whether it is atomy, we have two basic blocks. And then those basic blocks, we are going to instrument the beginning of it. Okay. Then after then we will try to open the file, then we have two more branches. Okay. Then for both branches, we will also instrument the beginning of those each branch. So for the multiple function, how many instrumentations we need? We instrument the beginning of the basic block. And we say 4. Right? So that's why we have 4 instrumentation here. Then the next function is print flag. Even though this function is not called by mouthful anymore, it will also be instrumented. If you can look at somewhere here, there are 2 cases, and both cases will be instrumented. Okay. That's why we are looking at 6 instrumentations in this program. That's why when you compile this, AFL tells you that we instrumented 6 different locations. That's the 6 different locations. Okay. So, how many passes are there on this program after all? As a developer, you develop the main function. The main function calls volatile, or called print flag, or make the print flag. That's it, right? AFL doesn't really instrument the same library in this case. Only instrument your part, because that is the part we want to find out. Then for this program, there are how many passes on it? Yeah, it's actually very simple. Only 3 passes, right? The first pass, at the beginning of the main function, go to F3, then it has atomy, then it opens the flag file successfully. That is 1 pass. After this pass, it will go back to main function and return, right? To the end of the main function. That's 1 pass. The second pass is the F3, the F open is not successful. Right? That's the second pass. Then the third pass is just even the atomy was not presented in that 3. So only 3 passes. Okay. Very simple. So we talked about where we instrument. We're going to instrument 6 different places for that simple example. Then we talk about what we are going to instrument there. Okay. So AFL idea is to get which edges have been taken. Try to encode that. So it's going to instrument the information to encode what edges have been pulled to view. It does that by instrumenting the beginning of basic block, which is called block. So it gives each basic block a random ID. Okay. And then random ID, random is a compiler. And one kind of a fixed ID. And that ID represents each basic block. Then you have one basic block goes to a different basic block that is an edge, right? So what it does is it will use previous basic block's ID to do an exclusive OR with the current block's ID. Okay. The previous basic block ID is actually shifted from its. I will talk about this later. Then we will indicate in the B flag that basic block, that edge has been used. So just in case that what. So here are the bitmap. Here is the bitmap. So this is directly taken from AFL's source code. So that bitmap in the default setting is a 64 kilobyte array. And each byte there represents the heat count of one edge. Since it's only one byte, so you can represent at most 255. If it's 0, it means this edge is one basic block to another basic block, have not been taken. If it's more than that, this means it has been taken, and it will not overflow. If it's 255, then you stay safe. So you do not mistakenly overflow it, so you think you have never been taking that edge. Yeah. So then how it works is we just introduce the two basic block IDs. And the way we are doing it is we use the shift to right one trick to do that. Let's say we have two basic blocks, A and B. They're IDs. If we just do 234 of A equals B, or B equals A, they will be the same value, right? But they are actually two different edges. A to B equal A are two different edges. So the trick AFL does is to shift the previous block's ID to right one bit. Then do explicit or with the current ID. Does that make sense? Okay. This is not perfect. Okay, but it's very fun. Okay. There could be collisions as well. Imagine you have a huge program. Your huge program has millions of basic blocks. Then there could be millions times millions, billions of edges. But in this approach, we can only represent 64,000 edges, right? So this approach is not perfect. So then we look at the instrumentation, which we, at the beginning of each basic block, and try to understand what's going on, how it works. It basically implements what we just described. Okay. The instrumentation here, this has nothing to do with business logic or real code. This is just instrumented at the beginning, like what we call regulatory instrumentation. Stack queries, right? In stack query, at the beginning of the function, we try to retrieve the query value from, remember, from thread local storage, TRF. Yeah. So here the same thing. We first try to retrieve the previous basic box ID from a thread local storage and move that to the register R14 here. So here R14, we get the address of that previous location's ID. And that ID is actually stored in TRF. That's why we're using FS here. I don't know if you guys remember this register, FS. We saw this before when we do that stack query, right? 64-bit, we use FS. 32-bit, we use another register. GS, exactly, you remember that. So then from here, we're actually retrieving the previous basic box ID to RAX. Then we are getting, so the third instruction, we are getting the bitmap's address. The bitmap is a global variable. All the threads share this global variable. We're trying to get the address and put that address in RCX. Then the next one, look at this one. We're doing inclusive OR of RAX, which is previous basic box ID with a hard-coded value, right? Look at here, this is a hard-coded value. This is a random value, hard-coded. It is random at compile time, And runtime this is already hard-coded. So this value represents this basic block. So here we're using previous basic blocks ID inclusive or with current basic blocks ID. Okay. So the value of that, we use that as an index. We will beat that to record if that edge has been taken. Or we just add one. Okay. How many times that edge has been taken? Okay. And we only have one byte for each edge. Okay. If we make it much bigger, it will be more accurate, but it may not be necessary, and it will consume much more memory. Okay. So the rest of this is just to add one to the occurrence of that edge in bitmap. After that, we will shift the current. Okay, so the current block ID in this case is 29006. Okay, we right shifted one bit. What do we get? We get 14. Right shift one bit is basically 95 bits. Okay? So that's why we get a 14503. Yeah, so this is also hard, right? And we save this ID as the previous basic block ID. So the next basic block, when we compute that, it will find this ID and inclusive always its own ID. Does that make sense? So if we go back to Binary Ninja, then you can say so the disassembly here look a little bit different, but actually there's a so this is the basic block ID of this basic block. And this is basically half of this. Okay? And then we choose to another basic block. So let's see if we can change this to decimal. If we change to decimal, we may find oh, it's not changing everything, it's just changing this basic block. Okay, whatever. Then here we have another basic block. And this is this basic block ID, different from the other basic block. And compile time is random, and this is half of this. Okay, makes sense. So that is how AFL instrument each function. Of course, AFL instrument many other functions. So those functions you can see here, those are for AFL's own bookkeeping and everything, and we don't talk about them today. Okay, so now we understand how AFL can track which branches has been taken, how many times has been taken, we record that in the feedback. There are actually a lot of math, but just remember, there will be math, there will be math. Remember how many times each branch has been taken. Okay? Then AFL will use that information to decide how we are going to mutate the input. The input started with something called a seed, and we can consider the seed as just some valid input we come up with. They're valid. AFL actually doesn't take invalid input. If your seed were crash the program, AFL doesn't accept that. They only accept seed inputs that do not crash the program. Okay. Then AFL has several different strategies to mutate the input. There are 6 different stages. Later, when we run this, we will be able to say the first thing is called it's a deterministic state. So for every input, it will do the same thing. It will just flip one bit or 2 consecutive bits or 4 consecutive bits of that input. Let's say your input is hello. 5 characters. Each character is 8 bits, right? So your input in this case is 40 bits. It will flip the first bit, then the second bit, or 30 or 40. So in total, it will generate 40 inputs from your seed. Your seed is five letters, 5 bytes. It will generate 40 more inputs from that. Then it will generate another 40 inputs by flipping 2 consecutive beats, then 4 consecutive beats. That's the strategy. It will also flip a byte, or so obviously flip here we flip 4 beats. Then the next step is flip 8 beats, which is a byte. It will also flip 2 bytes, 3 bytes. They are all deterministic. Then we will also try to add some values to some bytes. It will also change some bytes to some known integers, like -1 or x. The biggest number possible, change them to 0, because those are more likely to be corner cases, which may lead to crashes. Then you also have this havoc stage. They are going to randomly change a lot of it. They are going to change significantly by attempting usage, by chaotically to use it. Then there is another one is to surprise stage by combining multiple input together. Those are the strategies. So how do you run this one? The command we use is AFL file, okay? Not AFL clan file. That is the compiler. And you do not run the compiler program directly. So you compile program with your target binary. You do not just run that. You can still run that, but you will run that, you're not really running it. Instead, you fuzz it by using the AFL fuzz program. You specify what is your input. Use that -I input folder. In input folder, you will have your state input. Each input will be one single file. Then AFL will use the output folder to that. Where you have 2 items in your target program. We are going to run this right now. Let's see. So today I'm going to use my laptop instead of our server, because I don't think our server can handle if all of you run this plugin campaign on our server. So when you do your homework, you will be running on your own laptop instead of our server for this one. Okay, let's see, I'll make this a little bit larger. So this is my local folder for this overflow local 7. We have the main function, we have the makefile. I have several different versions of this program. One is compiled with GCC, another compiled with LLVM, then 2 different fuzzing versions. One is called AFL, another one is called AFL ASAN, which we will talk about later. So we are going to use this program to try to find the bugs, okay? So the command we are going to use, I put it here. We actually want to remove the output folder first. Let me leave the output folder. Okay, then also let me take a look at the input folder. So input folder, I have 2 states. Just call it state 1 and state 2. The name doesn't really matter. So state 1 is just a string hello. There's no new line after that. State 2, as you can see here, is the string admin, and also new line here. So the admin one should be able to give us the flag, right? So the first one doesn't give us the flag. Then let's run this further. This is the command to run that. We have to use the one we compiled, which is overflow. This one. We use this one to run the further. So now our fuzzer is running. It is generating different inputs, creating the program and try to crash the program, okay? AFL is trying to identify the crash. So let's try to see what information is provided on this UI. Processing time, how long we have been running this fuzzing campaign. 30 seconds so far. When was the last time we discovered new path? Not much. Okay. How many passes are there? Do you guys remember? 3 passes. Okay. And there's the overall results. There is total pass information. It says 2. Okay. So it has already discovered 2 passes. How many possible passes are there? 3. Okay. Have we discovered the third one? Do you remember what are the third one? Yes. So the third pass is actually enemy, but you cannot open the flag file. But in this case, we can always open the flag file. That's why you will never hit the third pass. That's why it says the total pass is only 2. And the AFL is complaining that it cannot find the new passes, saying it is all check the syntax file. But that's expected in this case. Then it looks for crashes. Does our program crash? No matter what you do again, our program doesn't really crash, right? Even if you override admin, it will not crash. That's a problem. So an AFL where considered crashing to be interesting, but in this case, we're not crashing. Then there is another information called mat density. What is the mat? The bitmap, right? So how many entries in the bitmap? 64K can represent at least 64K different edges. And how many edges we are hitting right now? Probably 3 or 4, right? Because the branches there, maybe 3 or 4 edges. That's why the map coverage is very low, only 0.01% today. And we're not discovering new edges. The count coverage there is not increasing. We're not discovering new edges. Then we have been running this campaign and running it for 620 cycles. Each cycle means we are running all of the input in the queue. And the queue is benefit from the input, starting with input. Okay? The input, 2 things, goes through all kinds of mutations, put it into a queue. If you find one input is interesting, we put it into the next queue. We have been going through 700 cycles so far. And let's see what others. The speed. We're running this program almost 6,000 times a second. Okay, that's very fast. Because the program we're under test reimbursement, and that is a good thing, right? We want the program to run fast, we want to test more input. So the bigger the number is better. Then here, now it is trying different strategies. You can say there's splice, we talk about, combining two strings. There is havoc, try to do chaotic mutation of that, try different that. The number after that is actually shows that for example, splice 5 means it was trying to apply splice on the queued input 5. Okay. So we are not really able to identify any crashes here. Also, we are using CPU 1 for this. My computer has 8 CPU, and we are the only one with CPU 6. And we are using 30% of the CPU resources. And here also shows the strategy, bit flip, byte flip, arithmetic, lower integers. We don't really have a dictionary, so we skip this one, and the havoc. And how many of them have to be able to identify it? So we can say now then, identify it. So running at 6,000 times per second. Yes. How is that related to the cycle? So the cycle includes many different inputs. It could be hundreds of inputs, several inputs, or thousands of inputs. And each input will be one execution. That's why the cycle number is much smaller than even 1 second of execution. Cool. So let's get out of this. Okay, so you'll notice a problem here. We know there's a box. And we're using the best pattern we know right now, but we're not able to identify the box. Why is that? The box is not crashed. It's not crashing together. So then we need to decide some method to make the bug manifest itself. To make the bug to talk to AFL in a language that AFL understands, which is crashing or hanging there, right? So that's why we need some other tools called sanitizers and or runtime sanitizers, and they can turn those silent bugs into very loud crashes. Okay. So sanitizers, they are also compiler features. They are not necessarily part of AFL. They are independently developed compiler type. They are used with AFL or other others. So we have sanitizers actually way before we have AFL. So the sanitizers we use right now, they are just a built-in implementation paths in UCC and AFL. And their job is to turn those silent bugs into crashes. You can label those by just adding compile flags like this. -f sanitize, and you can choose what sanitizer you use. And in my make file, the last one, we use the F sanitize address, which means we want to use the built-in sanitizer or a direct sanitizer for ASAP. There are many built-in sanitizers in GCC LLVM. The basic one is called ASAP, which we're going to use today. And ASAP can detect heap and stack overflows, can detect use after free, it can detect double free. So this one very familiar. You actually sometimes can also detect that into the volume. So like I said, volume will be much slower than this. Okay. And volume doesn't give you a particular input that can figure it out. So Fuzzing can do that. There is another MSAT, which will detect uninitialized memory read. There is a UPSAT for undefined behavior set. Basically, you are turning undefined behavior into crashes. For example, integer overflow. There is also TSAT to find the risk conditions of threats. There is also memory leak set. So those are built-in ones. We will only look at ASAT. And this is still a very hot area. Every year in all security conferences, we can say people proposing new sanitizers. So in the big picture is this part. So we use the sanitizer with the cluster. The ASAP was actually proposed 2012 in this Unix ATC paper. The authors were from Google, and you notice that this is published in 2012. This is actually 1 year before AFL was released. So those are two different independent efforts. Okay, we just happen to find by combining them together, we can find more bugs in a much faster way. Okay. The idea of ASAP is also quite simple. it will slow down the program by, I believe the paper said like 60% or 70% in most of the cases. In other cases, probably 2 times so much. We are much better than average 55. Volume is very slow because volume doesn't really execute the program natively. I mean, we were literal program with dynamic implementation and compile in a day. So for each instruction, that's why you can imagine the 50 times slower for each instruction. So the basic idea of ASAN is to use some kind of shadow memory region to track the state of every byte in your program. It will indicate whether this byte is readable, is accessible by a particular instruction. Here is a simplified version of this. It's actually much more complicated. So for our program, we have a buffer, let's say 16 bytes. Then we have adding, right? Without using AFL or ASAN to compile this, those two will be together. So your production system, you should put them together. So you do not break any of the memory in between, right? But what ASAN does is it will insert some red zone here, kind of like calories, okay? But calorie only works at the beginning of the function. You don't insert calories in the middle of any other two variables, right? So ASAN will do that. So if any, and this red zone should never be written by anyone. If there is any attempt to read or maybe even write here, it indicates something is wrong. Okay. Then it will instrument just abort function call there. Yeah, so the program basically just crashed, right? Then all variables, they will be read by those red zones. Okay. Even return address, say the RDB can do the same thing. It's much more complicated than this. For heap objects, you also need to indicate the status of that heap object. Is it free? Is it being used? Those kind of complicated situations. So if we compile the same program with ASAN, I already load that. Let's see. How do I get all of this? Sessions. So this is a ASAN version of the same program. If you look at the ASAN version compared to the AFF version of that, you first say there are many more functions instrumented here. Okay, many more sanitizer functions, ASAN functions. They use many instrumented there. Then if we look at the main function, volfoo is also getting much more complicated here. So this is the new volfoo, much more complicated before, but we still have the instrumentation that AFL has, which is the unique ID for each basic block, the computing the edge by using say or somewhere here. It should be here. It is a different approach, but it's saying, okay, yeah, that's how you can say that. Right? So the ID here, ID, somewhere here, we want to put, oh, here, that's an ID. This is what we like divided by 2 for this one. Right? Then you will also instrument every library function here. Take F open becomes underscore interceptor underscore open, F open. Okay. All those library functions are changed. But AFF functions are not instrumented, but library functions are instrumented. Memory set is changed to underscore ASAN memory set. So those functions now already able to detect memory corruption attempts. So if we run this ASAN version of this, first of all, ASAN use shadow memory, and the shadow memory is deep. Right? Because every byte in your original program memory where you need another byte or several bytes of shadow memory. No, I think it's every 8 bytes of your original memory will need 1 byte of shadow memory. Not seriously. So that's why if we just run it this way, it won't work. It tells us they do not have enough memory. So that's why you need to use the command here. M-long here basically means you do not have a limitation of how much memory this program can use. So let me remove that output folder first. We remove that output folder. Now we are going to run this ASAN version again with none. Okay. Now we are running the program. The first thing you notice that we identified a crash there, right? There is a unique crash we identified. We here only discover 2 passes, but that is expected. We cannot discover a third one. And let's say we actually discovered many crashes. We have already discovered 6,000, 7,000 crashes. Except that AFL believes they are the same crash. Okay? There's only one unique crash. So AFL use that feedback with the clock to assess whether they are the same. For different inputs, we will get different feedback. Like one kind of edges, which input has the trigger that is communicating the region. If the feedback is the same, no matter how many crashes you have, AFL says they are the same crash. That's why we already crashed the program almost 20,000 times. So is AFL like is it very here we're not actually doing that. So here, like you said, so at the very beginning, we only instrumented that 6 places. We're not instrumenting libraries. If you want to find the vulnerabilities in the library, there are several ways you can do that. First is you get the source code of the library, you compile that, right? Then AFL will instrument. So here we're not really compiling the library, we're just linking the library with binary, right? Another approach is there's a different version of AFL that you do not need to instrument anything. It works with emulator, like QEMU. Okay? So technically in QEMU, because of the emulator, then you can instrument everything because everything is under control. Then in QEMU mode, it's called AFL QEMU, then you can specify, I want to instrument this memory region. Then you can say, I want to instrument the C library memory region. The approach it uses will not be this kind of a compile time instrumentation. It will be dynamic instrumentation, so same or similar of what the Valgrind does, which means it will be much, much slower. Yes. But the benefit of that is you don't need the source code with binary condition. So in firmware fuzzing, where our lab works on, sometimes we have to do that because we just do not have the source code. Yes. So go back here, let's say, well, Patrick was able to identify the issue once. So what I can do is 8 K times already. Let's say anything else to do. Not much, huh? We just identify one crash. Then let's take a look at that crash. Get out of this. So everything AFL will save that in the output folder. So in output folder, it will show for the last campaign, Fuzzing campaign that we run so many cycles, running so many different people. What edges will be covered, so that will be the first, the left part. Then what crashes were being identified, let's say crashes. So here, it only saves the unique crash, and there is only one unique crash. And the name of this, the content of the file indicates the definitely. And the name of this indicates how we get that input. The IP0 here means we generated this input from the state there. The state what? The first state, okay? Then the crash ID or whatever crash we get is the signal 6, which is saved abort. So that's not segmentation board, but saved abort. And the signal board was implemented by assembler. Then, oh no, sorry, the source is actually from the first state. ID means this is the first unique crash input. Then what kind of operation in here? We do that random chaotic mutation from the first state and get it from, and we repeat this 16 times together. So let's see what input it actually, what is the input is actually generated. Crash. Oops. Okay. So our C, if you remember, our C was hello, 3, 5, hello, right? By adding all kinds of mutations, eventually, AFL generated this input. Oh, you can still see something from here, right? The H, adding a lot of garbage here, adding garbage mutating differently. And this was the first random mutated input that eventually crashed in the program. It looks much different from the original input already. And it will be difficult for us to manually craft something like this to identify that. Okay. Cool. Let's see. So this is from a different campaign, but as you can see that it generates a different input. Okay. It also crashed the program. Okay, so let's take a 10 minutes break. Then when we come back, we look at much more complicated cases and find more bugs. Yeah. So we come back 7:40. This is the hearing closure of everything. If you want to but I think it's basically what happens every Or I'll do it later. So basically, I usually do this to work with poetry. I just work with the But the problem is that I know people want to upgrade with a few different outlets, right? But you're going to miss out on that. That's a bit different. That's how you can go wrong from they're the best like out of the box. Like, the Nova is surprisingly very good at that. Yeah, I think I do like this thing we not go over the time. Things that are also more similar about like especially the one thing that you cannot it's the making sense. It's a fun. I think that's that's a robin. That's well. Yeah. If you are the mind factor is right. The other factor is they're going to get fun. I don't know what I'm doing with very kind of it's been work that I would want to affect. Mind from the arrow and happy again. The problem is
Okay, let's keep going. So
before we can finish early today. So, more complicated takes. That's it. More where you more this to show how I identify more box. I give you some time to read it first. If there is one time box, you can identify here. You have the main box there. We define a structure for cafe. Cafe has pointer, which is a name, and that name, this is just a pointer, that's just an address. The name, the buffer itself will be annotated on stack. So this is very similar design of each. I'll just be going to the last of the next here the first or second by the keep in the same okay. So every time you have a string, you allocate some space on the heap. And do that with string group. The C library function string group do that. So here we do the same thing. Okay, we will find a way. So the structure has name, which is a pointer, age, the score. We'll also have a command, which is right. Exercise. So every something like that, we can, that could be a buffer. Then there's a function called the set name. That will give you the address of a config and a string. We try to set that. The first, we could create a local buffer to 64 bytes. Then string copy to the local buffer of the 6. There could be a buffer overflow, right? You can overflow that the buffer. You can overflow the return address. That's a box, right? Then it will try to use the C library functions in here to make a copy of that string, right? And the string group will allocate memory on stack, which means at some point you should free that memory, otherwise it's delete. Then assign that address to name. That's the thing. Then print, where just a print the name, print the age, and print what. Do you see any vulnerability here? Do you see any vulnerability here? For print. Okay. The marking says no. Right? Any other idea? Do you see any problem here? Format string, let's say. Not really. Just all three strings are outputted. Right? So in format string, the attacker needs to transfer the format string. So here we'll pass it on to this. Any other bug you can think of? Okay. There could be a null pointer dereference, or even more. The config itself may not be a value address, right? It could be a null pointer, and also the name will also be a null pointer. If you put this print config before you set name, then this one will trigger a null pointer dereference is eventually a segmentation point, right? So that is another box. Then set the score. Anybody here? Oh, yeah, yeah, actually, okay. So there could be a divide by 0 dot. Okay, right? The score could be 0, and 100 divided by 0. Set command here, let's say, have the buffer overflow as well. Because there's a string copy. 50 watts there. Also, the string copy. This one will not be. It's going to be all the info really box because it's going to be allowed. The pass line there, let's say, get a line, length of the line. I do not say always constant, I will include. And then there's the memory sets. So this memory set will initialize the name pointer to 0 to null. That's how you could get a null pointer to reference there. You will just get it in get the input from std, then you create that. So for this program,
we already say several bugs. Then let's use AFL, try to discover them automatically. So I already created 4 states here. Well, I already created several states here. And this, like I said before, states are supposed to be valid input without crash program. So, it's not really good. The states are just the name equal to annex, page 25, something like that. Okay. So that's a six. Then let's run a campaign here with obviously with ASAP. We're going to run ASAP. Parser. Okay, we have started this. We already find one crash there, a unique crash. We already find 29 passes. As you can see, this program has many more passes. But depending on what you see, there's not compared, screen compared, you can compare what you see that from the set here, right? So many more passes from the program. Discovered already 34, find 8 unique spots already. Find 700 crashes already. Your map density is still small, but that is only because the program is here. The program is here. Even though we have, in this case, probably 30 spots. The transition between them will not be 400, because not every dot they can get will essentially be 100. Right? So that's why the map density there is still low, but much higher than what we had before. So even deep is generating some crashes. Lower integers is generating some crashes as well, and the average more crashes generated. So we identified 8 unique crashes so far. So by the way, some of the fuzzing campaigns we will run them for days, several days. Because sometimes it's very slow. Let's stop this. Then let's take a look what we have here. Crashes. So here we have 8 unique crashes, and all of them with our and they are from different states. The first one from state 0, another state 2, 2 from state 2, 1 from state 3, and this one was not from our original state, right? It's from input generated from state, and then eventually, so it's not directly from state. Then with our operation, it eventually generates that input. So let's take a look. Each of them. Output. Okay. So the first sequence we have is, so you notice something. We have the input that generated the flag, right? But AFL doesn't really tell us explicitly what box it is, right? But we do have the input that can replicate that. So if you really want to understand all this, what kind of box it actually figures, we take this input, we debug the program, we debug that step by step, then we can understand where exactly that crash happened. In this case, it looks like just the name is too long, maybe. Yeah. The name is too long, it may overflow the main field there. Then another example,
7. This example,
This one started with 8. So 8 is not supposed to be in half here. I'm not really sure why this one goes crash. That's why there is another research area. It's called root cause discovery of it. After you find it, you can trigger the bot. You devise some automatic approaches to explain exactly why this triggered which bot and where. Right? So this one doesn't really say. That's not for
so we can see there are many different. Let's check one more. This one is also a name. Oh, this one is interesting.
So this one, yeah, this one will be big. So this part where you're not saying video, this part is not so this part. Okay. Those are not easy to plot if you just manually create those designs. So what do you think are the differences between writing the test cases and you have been developing software for all 4 projects and for all of the projects you have been writing test cases, right? How is that different from fun? Okay. So we are saying is you can only come up with limited numbers of test cases, right? What else?
Let's say the problem with problem in the three, the problem we don't.
That's a very good point. Yeah. So, yeah. Finishing the decided in the and most of the test cases you are dividing, you are testing the cases that they should work out. Right? You're not testing, you're not trying to find, there are cases, you are trying to find cases that they may malfunction or trigger from other cases. But those are very important. Here, we're only looking for those cases and the unexpected. So that's why we have to take it to feel necessary, but we some a different purpose.
So that is basically what I have for today.
So today is going to give you like a little bit so what automatic thought discovery and neglect. So those are the topics I will cover in the master software in the top. I think I'm not answering that in the second step. It will be next year. We will talk about all kinds of, for example, even sanitizer. We can spend a week just by how they are implemented, how they can be optimized. You can see the ASAM we're using right now, still quite slow. There is a recent paper, maybe last year, from one of my friends. So the significantly reduced the cost of the sanitizer. So they do program analysis and explain that not every place you need to instrument. There are many places where the instrumentation will actually be equivalent or redundant. So you just need to make them much more faster. So AFL itself has many different research units. But here we're talking about applications. So how do you pass the channel? How do you pass firmware? how do you, network code? Let's say, there's a security IP server, there's a web server with only contact. You cannot use mutation strategy where you can get it. Because those network packets, they have very strict form. Every single has many. If you think a little bit, you're posting down in Excel, so you're even checked by that. Then, more easy, you only reach a very general state of the program. So, for those cases, what we do it, for cases that you do not have the system, you only have the binary code, what you can do. For cases that you do not even have the binary code, what you can do. So we have an ongoing project right now in our lab, where our model is we do not have full code, we do not have firmware, so we cannot reinforce it on any kind of emulator that is such a here. Then we use electronic magnetic signal. We have our embedded system, which is a probe on top of that, we pick up EM signal and use that EM signal to infer what kind of basic signal it has been executing, and we use that and guide the AFL to generate the process. So, all kinds of research can be done in this kind of project, and also when we're talking about something like the Walgreens, that's a very interesting project. There's a long time ago we had a project, however, it's very slow, very powerful. So for any program you are running, the Walgreens will list it to its own intermediate language. The instruments in that language, so every instruction will list it, instrument it, recompile it into x86, then execute it. So the program will never execute it in place. Every instruction is listed, translated, then turn it on in place and execute. Very slow, very effective as well. So those guys do that, it's amazing. Very complicated program to do that. Then there are other techniques we use, like symbolic execution to find what kind of conditions we need to meet. For example, look at this program, right? So if we want to trigger a particular branch, we can randomly generate the input, or we can symbolically execute the program and try to record or maintain the condition that we have to meet to trigger a specific branch. And that condition is represented in some kind of mass formula. Then that mass formula is given to some kind of a theorem solver to solve it, to give concrete examples when we try to solve it. So symbolic execution is widely used with solving as well. There are many different things we discussed in the advanced software solution. But I do require that the students take this class first. You have to know how to manually hack first before you go to automatically code. I thought large language model or AI is playing an even more important role here in hacking. I think I told you guys before, we are developing an agent to hack all the challenges in this class. And so far, our agent already captured the 80% of the facts in this class. And our goal is that agent one day can participate in CPF, which is the Olympics. So if some of you are interested in that project, and you're welcome to contribute as well. Yeah. So what we discussed for today will not be in the exam, and there will be one more class next week, and we will talk about cache side channel attack. If we have time, we will also watch a video together, depending on if we have the time. The video talks about memory-based programming such as that. If we don't have time, then we can cover that after. So the final CTF will only cover the attack part, format string, heap, walk, and maybe a other reverse engineering kind of that's what we're going to do. Any questions?
I don't know why it's so slow today. When I talk,